Consider the following system of linear equations. x2 minus 5x3 is equal to 6. 2x1 minus 2x2 plus 11x3 is equal to minus 12. 4x1 minus 3x2 plus 17x3 is equal to minus 18. A. Use Gauss-Jordan elimination to put the augmented matrix corresponding to this system into reduced row echelon form. B. State which variables are free and which are basic. C. Find any solutions of the system. D. Give a geometric interpretation. So for part A, in order to find the reduced row echelon form of the augmented matrix, I need to write the augmented matrix. So augmented matrix is... Okay, so, and this is for part A. So, my augmented matrix has a column for each of my variables, and in those places I put the coefficients from the equations, and it has a column for the answers on the other side of the equal sign. So, that shouldn't be too hard. So, my first column will be for x1, and then I can write the whole first equation in the first row. So, I start with no x1s, and 1x2, and minus 5x3s is equal to 6. And 2x1s minus 2x2s plus 11x3s is equal to minus 12. And 4x1 minus 3x2 plus 17x3 is equal to minus 18. So there is my augmented matrix. Now, what's Gauss-Jordan elimination? That means using elementary row operations. So since I'm going to have to do elementary row operations, I'm going to need some space. So I'll start a new page. So my matrix was 0, 1, minus 5, 6, 2, minus 2, 11, minus 12, 4, minus 3, 17, minus 18. And the first column was for x1, and the second column was for x2, and the third column was for x3. And I'll write the matrices that this changes into from the row operations below, and I'll continue as I go. So I need to get to the reduced row echelon form, and the reduced row echelon form has a 1 as the first non-zero entry in every row, and all of those leading ones, they're called, have zeros above and below them, and all the rows of zeros, if there are any, are at the bottom. And what that actually looks like in the end is that you end up having columns of the identity matrix. And between, you have as many as possible, and between them there are some extra columns which have zeros in the same places as the column before. So that's what we're looking for. We're looking for columns of the identity matrix. So what we want to achieve by using row operations is to get this column to look like the first column of the identity matrix. Right, so that means I need a 1 in this position right here. Now my options are, using row operations, I can swap rows, I can multiply rows by constants, and I can add multiples of rows to other rows. Now, many of those things could get me a 1 here, or at least something that's not 0. Multiplying isn't going to give me a 1 there, so I definitely have to either add another row to this or swap, and swapping is much simpler, so I'm going to swap so that I don't have a 0 in that spot. So let me swap row 1 and row 2. So my new row 1 and row 2 are my old, row 2 and row 1. So let's see. 2 minus 2, 11 minus 12, 0, 1 minus 5, 6, 4 minus 3, 17 minus 18. I've swapped the first two rows. So now let's just move this. I want the first column of the identity here, and I want this entry here to be a 1. Well, that's not hard to achieve. I can just divide by 2. So my new row 1 is equal to half of my old row 1. So let's see. 1 minus 1, because negative 2 divided by 2 is negative 1. 11 divided by 2 would be 5.5. And 12 divided by 2 would be minus 6. And I haven't changed any of the other rows. So I'll just copy them back in. And now I want, again, the identity here. I already have a 1 in the right spot. Now I want zeros below it. Already got a 0 there, so that's good. Now I want a 0 here. Now, I can't get a 0 there by multiplying the whole row by 0 because that would lose solutions to my equations. The only way to get a 0 there would be to add or subtract a multiple of another row. And I've got a handy dandy 1 right here to use. So I will do, to get my 0 in this position here, I will do my new row 3 is equal to row 3 take 4 of row 1. So I haven't changed any of the other rows, so I'll just put them in. Okay, so in this first position, 4 take 4 times 1 is 0, so we get the 0 that we wanted. Negative 3 take 4 times negative 1 would be negative 3 plus 4, which would be 1. And 17 take 4 times 5.5. Well, 4 times 5 would be 20, 4 times a half would be 2, so 4 times 5.5 is 22. So 17 take 22, which would be minus 5. And then negative 18 take 4 times negative 6 would be negative 18 plus 24, which would be 6. And that's where I am now. So I have the first column of the identity. Now I want the second column of the identity here. Now if this row column was all zeros, then I couldn't achieve the second column of the identity. If I actually had this like that, then I couldn't achieve the second column of the identity either, because while I would want a 1 here and I could get it by swapping the first two rows, that would destroy my first column of the identity that I wanted. So the general principle is once you've got your first column of the identity and you've moved down the diagonal to look for the next one, you can't swap rows from above, or add multiples of rows from above, because it will destroy your beautiful zeros that you created here. So I just need to remember that fact. But I don't need to worry about that for the moment, because what I want is a 1 here, and I already have a 1 there, so that's good. So now what I want is zeros here and here. Zeros in those two positions. So how am I going to do that? I'm going to add multiples of the middle row. So this row here to the other two rows. So I would like there to be a 0 here. So I would need to add on row 2 so that minus 1 plus 1 gives me 0. So my new row 1 will be equal to row 1 plus row 2. And I would like a 0 here as well. So my new row 3 would be row 3 minus row 2. New row 3 is equal to row 3 minus row 2. So let's see. Let's keep the answers the same as they were before. We haven't changed the middle row. That's the thing that hasn't changed. That's what we need to keep the same. So row 1 plus row 2. So 1 plus 0 is 1. Negative 1 plus 1 is 0. 5.5 minus 5 is a half. Minus 6 plus 6 is 0. And then my new row 3 is row 3 take row 2. So 0 take 0 is 0. 1 take 1 is 0. Minus 5 take minus 5 is 0. And 6 take 6 is 0. Alright. So now what I want is I already have my first column of the identity here and my second column of the identity here. So I want a third column of the identity here. So I would want a 1 in this position and zeros above it. But I can't get a 1 into that position because the only way to do that would be to swap rows from above or add multiples of the rows above, and that would destroy my beautiful zeros here. Remember how I said you can't use rows from above? So I can't actually get a 1 here, so I can't get my column of the identity. So that's as far as I can go with my reduced row echelon form. And let's just check that it's in reduced row echelon form. For reduced row echelon form, the first entry in every row ought to be a 1. The first non-zero entry. So in the first row, yep, first entry is a 1. In the second row, yes, first entry is a 1. And in the last row, well, there are no non-zero entries, so that's okay. And the other thing we have is that there are zeros above and below all of those leading ones. So there are zeros below this leading one. Excellent. There are zeros above and below this leading one, and that's the last leading one. In the end, it's supposed to look like there are columns of the identity, and between them every other column has the same number of zeros below as the previous column. So you look for the column of the identity here, and it's got 1 0 below, so this one ought to have 1 0 below as well. Alright, so it's definitely in reduced row echelon form. So we've completed part A. Now I suppose technically we should actually write down exactly what the reduced row echelon form is, because the question asked us to do that, so we will do it as well. So the reduced row echelon form is 1 0 a half 0 0 1 minus 5 6 0 0 0 0. That's the reduced row echelon form of the augmented matrix. And now we can do part B. B says to state which variables are free and which variables are basic. And to do that we need to look for those leading ones, or those pivots as some people call them. So let's look for them in our reduced row echelon form. There's a pivot, a leading one here, and there's a pivot, a leading one here. These are the columns that are the columns of my identity. And once I've circled my pivots, there are some columns which don't have any pivots. This one here. I don't need to worry about the answers column because I'm only looking at my variables. So the variables that correspond to those columns with the pivots are the basic variables, and all the rest of them, the ones that I've circled, the variables with no pivots, they're the free variables. So Those first two are x1 and x2. So x1 and x2 are basic, and x3 is free. Right, that means we can move on to question C. So question C is to find any solutions, if there are any. So the way to do that is to think of these things as equations again. So I'm first going to look at the bottom row, because that's the row, the one with all the zeros in it, that's going to tell me whether there are solutions at all. The bottom row of the reduced row echelon form corresponds to 0x1 plus 0x2 plus 0x3 is equal to 0. And so that's just 0 equals 0. Nothing wrong with 0 equals 0. But the point is, if this number here had been, say, a 10 instead of a 0, we would have gotten 0x1 plus 0x2 plus 0x3 equals 10. 0 equals 10, which is wrong. That's not possible. And so if that had been a 10, there would be no solutions at all. But there are solutions, possibly, there are solutions, because it's not a 10, it's a 0. Oops, sorry. Alright. So, solutions certainly exist. How do we find them? Well, we can look at the other rows now. The other rows would correspond to equations like this. So we could have an equation x1, 1x1 plus a half of x3 is equal to 0. And 1x2 minus 5x3 is equal to 6. That's the equations I'm left with. As you can see, I can't quite figure out what everything was. If these had all been 0 just here, if these had all been 0 just here, then I would have been able to say it's just x1 is equal to 0 and x2 is equal to 6. But they're not equal to 0. But that's okay. If I knew what x3 was, I could figure out what x1 and x2 were. If x3 was, say, 4, then x1 would be minus 2, and x2 would be 6 plus 20, so it would be 26. But the thing is that x3 could be anything at all, and the solutions would still work. That's why it's called a free variable. It's free to be whatever number you want it to be. So in order to solve the equation, you find your free variables, and you say, let x3 be equal to t for t in R. If there'd been two free variables, I would have let the other one be maybe s. They're not allowed to have the same letter because they're not necessarily the same thing. And then using our equations, I can write x1 and x2 in terms of t as well. So that would mean that x1 plus half of t would be equal to 0. So that would mean that x1 is equal to minus a half of t. And this would mean that x2 is equal, minus 5t is equal to 6. And that would mean that x2 is equal to 6 plus 5 of t. And so we can finish off our solutions like this. So, x1, x2, x3, we put them in a vector like this, is equal to, well, let's see, x1 was minus a half of t, x2 was 6 plus 5t, and x3 was t. That's what my solutions look like. For some t in R, that's what all the solutions look like. for t in R. And that's my answer for C. Now it is possible to write that solution in a slightly different way, and there's actually a traditional way to write it, which I'll show you now. So my solution was so far x1, x2, x3 is equal to minus a half of t, 6 minus 5t, t. Now what I do is I split that up into two different vectors, two different column vectors, with all the t's in one and all the numbers in the other. So let's see. I'll put the t's over here. So minus a half of t, minus 5t, t. And we've got 6 minus 5t in the middle. And the other numbers here must be 0. 0 plus minus a half of t, and 0 plus t. And then for this vector that's got the t's in it, 0, 6, 0 didn't change, I can bring the t's out the front, because you can always multiply a whole vector by a number. Minus a half, minus 5, 1. That's the traditional way of writing it, because it helps us understand what the answer looks like when we attempt to interpret it geometrically, as we are supposed to in Part D. So give a geometric interpretation. Well, in order to interpret these things geometrically, we need to think about what the equations stand for and what the solutions stand for. So because we're working with three variables, we must be in three-dimensional space. This point here has three coordinates, which means it's a point in three-dimensional space. The equations, therefore, being linear equations, represent planes. A linear equation in three-dimensional space represents a plane. And the way it represents the plane is this. The way to tell if a point is on the plane is to see if it satisfies the equation. So the plane is literally all the points which satisfy the equation. So we can say the three equations represent represent three planes in 3D space. Okay, the solutions are points because they're vectors. And a point which satisfies one equation would be on one of the planes. A point which satisfies all three equations will be on all three planes. So the points, the solutions, points which satisfy all three equations, so there would be points which are on all three planes, and so the solutions would represent the place where the three planes intersect. So the three equations represent three planes in 3D space meeting in, well, they have to meet somewhere. They meet in the set of points, which is the set of solutions. So let's have a look at these solutions. These solutions are a point, 0, 6, 0. So that would be the place where we start drawing our solutions, plus t times this vector. So what that would mean is that we start at the point 0, 6, 0. And we add on minus a half, minus 5, 1, which would move to a new point. And then we'd add on 2 of that, and 3 of that, and 4 of that, and minus 2 of that, and minus 1, and a half of it. And if we add on enough of those, we'll be able to see that it makes a line. This set of points is a line in three-dimensional space, which you would expect. You would expect planes to meet in a line, though three planes could meet in a point, or it might be possible that there's no point in all three of the planes. And that would correspond to different types of solution. But at the moment, we've got a line as our solution. So the three planes represent So the three equations represent three planes in 3D space meeting in a line. And that's my geometric interpretation.